Good morning, good afternoon, everyone. Thank you for joining us in today's webinar. We are going to talk about mechanical reliability, which is part of the series on ANSYS solutions to help improve electronics reliability. So, electronic systems are found in nearly all industries: aerospace, automotive, consumer electronics products, healthcare, industrial, and many others. As such, ensuring these systems remain operational and perform their intended functions in a variety of environments is critical to product success and customer satisfaction. Companies who properly address electronics reliability concerns, especially through simulation, can meet any of the objectives stated in this slide over here. Traditionally, companies have used a design, build, test, break, fix it kind of design cycle. However, such an approach can be expensive, and we just came out of a meeting where it is proven that it is expensive. And the customer in this meeting was looking for a faster and also a cheaper way to do this product development. So further, these design rules and best practices may not provide engineers with enough guidance to properly design modern cutting-edge products. By using simulations, specifically ANSYS solutions, virtual models, prototypes can be created and simulated in virtual testing. This will help provide engineers with a higher degree of confidence that the physical tests they do run will be successful. ANSYS provides a suite of tools and workflow solutions that address a wide range of electronics reliability concerns. Each aspect, electrical, thermal, mechanical, multiphysics, and reliability physics analyses plays a key role in the understanding of how electronic systems operate and perform in a variety of situations. So we did do the electrical reliability webinar on June 9th. The recording is available. If you're interested, please let us know. Last week we did thermal reliability. This week we are doing mechanical reliability. And next week we are going to talk about comprehensive multiphysics solutions. And the week after next, we are going to talk about reliability physics analysis. That's on July 7th. Please sign up for these on our website. So today we are going to focus on the mechanical reliability and being physical structures, PCBs and other electronic components are susceptible to failures due to excessive deformation or warpage. And this may be from thermal loads and excessive shock, vibration, drop, which we tend to drop. I tend to drop my phone a lot. So with this, we have solutions, ANSYS have solutions to address these all one by one. One by one, meaning that we can do tumble test simulations, we can do drop test simulations, we can look into moisture simulations and how it affects, and we can also address the solder joint reliability. And in this webinar, we are going to talk about how we can take into account all these details in our models. Details being these traces, as well as coatings, underfill, because they all play a role. They either enhance or decrease the fatigue life. So when it comes to mechanical reliability, the simulation challenges could be the geometric complexity. As you see here, on a board, there's really many components. And when we look at inside the board, we have different layers. On every single layer, we have these different traces. So it is really a complex geometry. And then we have material complexity. On a PCB board like this, these components, they have different materials, and each of them behave differently under different thermal conditions. So we need to be able to specify material properties as a function of temperature. And in addition to that, some of these components on PCBs, they do creep, meaning changing shape over time. So we need material models that will take into account all of these nonlinearities. And then we also have the physics complexity. We need to be able to determine the electrical field, the high frequency field, and the high frequency, even the low frequency, they will do Joule heating. And Joule heating is going to start heating the boards. And when it starts heating the board, it's going to expand thermally. And then we need the structural coupled physics to be able to understand how it expands, how it warps, and so that we can predict its behavior over time. In addition to that, we have shock. We should be able to do simulations of shock, drop, impact, vibrations, and then thermal and humidity solutions as well. So ANSYS tools have the best-in-class PCB modeling capabilities. As you see from this picture on the left-hand side here, it used to do, we have the capability to do lump mass modeling. What that means is, years ago, and even today, if we need to do a very quick simulation, what we do is we take the model and then we lump the material properties. And if we can we can lump it in one material, in one element thickness, or we can even specify multiple layers by lumping these material properties. So if we look at the picture in the lower right-hand corner over here, the vertical axis shows the speed. The horizontal axis shows accuracy. So with the lump approach, we are doing simulations really fast, but the accuracy is not quite there. So the next level from there is trace mapping. So from ECAD data, we can actually read in the geometry, and we can map the material properties from the ECAD geometry. We can map the material properties onto a given mesh, so that when we look at the material plot of this mesh, due to the presence of different materials, the mesh is going to have different material properties assigned to this. So this is what we call element-wise material mapping. And that's another solution. And as you see here on this chart, the trace mapping approach, which is this approach over here, it is fast, and it's more accurate compared to lumped approach. And then reinforcements. This was introduced last year. We can bring in traces, vias, and as you see here, it's going to improve the accuracy. And these reinforcements is going to give us a higher accurate solution, but the speed is going to come down. Why is the speed going to come down? Because we are really accounting for a lot more complex designs over here. And then we have trace modeling. With trace modeling, then we are bringing the full three-dimensional detailed geometry of a PCB, and we are modeling it. As you can imagine, this is going to model every single trace, every single layer. So it is going to have a lot of nodes, a lot of elements. And when we look at the accuracy versus speed, the speed is going to come down. Why? Because we are going to have a big model, maybe of the order of 10, 20, 30, 50 million nodes. But our accuracy is going to go up. So that's why this trace modeling approach is in the lower right-hand portion. It's highly accurate, but the speed is going to come down. So, but ANSYS provides all of these options to you. And then when it comes to these detailed component modeling, as you can see here, we can take into account the wire bonds. We can take into account the solder, meaning that we can put a lot of nodes, a lot of elements in every single solder joint. And we can, the leads here, similar to wire bonds, there are hundreds of leads, but we can model all of it one by one. And of course, traces, vias, heat sinks with all the greater details and underfill. So ANSYS has the capability to be able to account for high-level details. And then these are some examples of once you have that complicated geometry, and even if you don't have the complicated geometry, if you're using the lump mass approach, you can do warpage simulations, and the solder reflow warpage simulation, you can do step-by-step assembly process. This is where we use advanced capabilities such as what we call it EKIL, ELI, element birth and death features, so that we can take into account the process itself as to how all these components on the PCB are put on it, and we can track it step by step. And at the end, as these components are being soldered or being replaced mechanically or through soldering, we can actually predict the warpage on this PCB. And then tumble test. We can definitely simulate that. We can do shock and vibration. This could be shock and vibration. Shock is in time domain, and vibration could be in time domain. We could do it in frequency domain. We can even do power spectral density type of simulations if we know the excitation. And then, of course, drop test and moisture effects. Moisture effects can be accounted for, again, in a lot of detail. You can take a very detailed PCB assembly, or you can do it at package level. Here we are looking at a moisture simulation at package level. And then we can also do the fatigue and fracture calculations. We will talk more about that. The fatigue calculations can be based on viscoplasticity methods, and the fracture can be based on just either delamination or fracture itself. And, talking about the board level warpage, we do have the means to be able to do the solder reflow simulation. Why is this important, the solder reflow? Because as you see here at the beginning, the solder is started out as a rectangular block, but during the reflow, it's going to melt and it's going to take a certain shape. And then once it takes a certain shape, it's going to solidify. And we need to be able to capture that solidification and the final shape to be able to do a really complicated fatigue life simulation or warpage predictions. So ANSYS, this is done in ANSYS Fluent. And this is important because, again, it's going to affect the warpage, the package, or the PCB warpage calculations and predictions. So, and also just to show you another one, this is a paper that we presented many years ago. So again, you can use either ANSYS Fluent or ANSYS CFX to calculate the final shape of these solder joints. And these simulations are done in our CFD models because this is a VOF, volume of fluid simulation, where the tension, surface tension of the fluid becomes really important. The surface tension is going to the surface tension is going to determine its final shape, and also the contact angle it makes on the solid itself. That's also important because it's going to determine again its final shape. So from this animation, you can see that there are two different walls on this pad over here. One of them is hydrophilic, the other one is hydrophobic. The green one is hydrophobic because you don't want the solder melting out and expanding to the green area. And the blue area that you see underneath is the hydrophilic surface. And you want that expanding in that region, but you don't want it going into that other region. So, and then ANSYS has both implicit and explicit capabilities. Where do these methods they come in? Implicit methods and explicit methods overlap if there is a transient event that's happening of the order of, say, seconds, 1 second, for example. We are talking about an event that's happening over a second. Then implicit method, you can use ANSYS implicit methods or ANSYS explicit methods to do the same phenomena. ANSYS mechanical is an implicit solver. ANSYS Elestina or ANSYS Autodyne is an explicit solver. So explicit solvers really are very powerful when we are doing ballistics, detonations, blast simulations, hypervelocity impact simulations. As you see, these things happen of the order of milli to microseconds. So if an event is happening of the order of milli and microseconds, then you definitely want to use explicit methods. And if an event is happening over more than a second, like 10 seconds, over years, like creep happens over years. It doesn't happen instantaneously. It does happen over a long period of time. So then you can use ANSYS mechanical because ANSYS mechanical has really good creep formulations. There are 13 different creep formulations, and in addition to that, there's viscoplasticity formulations in ANSYS mechanical. Again, viscoplasticity creep, they take over long periods of time. And shock and vibration, vibration, actually from when we talk about shock and vibration, the very first thing we have to do is do a model analysis. Why do we do a model analysis? Because we do want to be able to predict the mode shapes and the natural frequencies. The natural frequencies are going to determine how our structure is going to respond when excited at certain frequencies. So that's why we do a model analysis first, and then we do either a shock simulation, which could be short duration, high pulse excitation. These are done in time domain, or we can do harmonic or random vibration simulation we may have a very sensitive PCB assembly like this, and when you ship it or when you handle it, say it's put on a truck from the factory, it's sent over to the airport by truck, and then at the airport you put it on an airplane. So all these data, there is actually data. If you put it on a truck, there is a PSD excitation data, random vibration data for shipping on a truck. Then when you put it on an airplane, there's a different curve to do random vibration for plane transportation. There's even one for helicopters. So you can simulate all these events one after another to see if your sensitive electronic equipment is going to be affected by transportation, by shipping, by handling. And if it's subject to a sinusoidal event, like a sinusoidal load, if this is put on a rotating machinery, then we have to do a harmonic frequency simulation and try to predict the life of these components, see if they will prematurely fail or if they will fail at longer periods of time. It doesn't matter if it will fail over longer periods of time. We do want to know how many cycles is it going to take, 5,000 cycles, 10,000 cycles, or 20,000 cycles for these components to fail. And drop and impact, again, these are mostly handled in our explicit simulations. And we also have ANSYS motion, where you can actually do the stumble test in ANSYS motion. And along the lines of drop and impact, we have done our simulations in the past where we look at a phone being dropped, and we want to be able to predict the crack, the angle at which the crack will propagate. And why do we do that? Because then we, from experimental results, here we are looking at dA over dN on the vertical axis. dA stands for, crack length, and then on the horizontal axis, we are looking at maximum stress intensity. That is the crack. At the crack interface, we can actually look into the stress intensity factor and see if we ever have a crack in our phone, how it's going to propagate over time. And there is experimental data that shows how these cracks will propagate on our phones. And you can see it. If it doesn't totally fracture, and if you put a crack in there, like I did it yesterday on my phone, you can actually predict how many more times you can drop your phone before it goes to complete failure. And we have even taken a cell phone and dropped it, and by using sub-modeling technique, and this is all done in LS-DYNA. In LS-DYNA you can do sub-modeling, and you can look at the solder joint connections during and after you drop it, and then from these drop test simulations you can actually predict which solder balls, which solder joint connections are going to fail, and you can predict that which ones are going to fail after how many milliseconds. And in this case, you can see one of them failed after 2.5 milliseconds. So these are all possible. We have fast computers. We have the technology like LS-DYNA to be able to do this. And in addition to that, we can also simulate the moisture absorbed by packages during storage. Yes, during storage, especially if you're in a humid environment, these packages, electronic packages, are going to capture the moisture. And what's going to happen is that it is going to affect, and it's going to cause some warpage, and it may even end up in delamination, meaning that the different layers will delaminate, and it can lead to this what's called this popcorn effect. So all of this can be simulated. And how do we simulate that? We simulate it in ANSYS Mechanical by using coupled field elements, which is a simultaneous simulation of thermal, structural, diffusion physics. And here the diffusion is really the moisture, because moisture is going to diffuse inside these layers. And using the fracture capability, as you know, in ANSYS we have classic fatigue techniques, which is used in stress life and strain life approaches. And we can also calculate fatigue due to harmonic or random vibration. So we can do a PSD random vibration simulation and then calculate the fatigue life. And also, if there is any crack implemented, we can predict its crack path. Well, once it starts running, which way is the crack going to go? We can definitely simulate the crack failure. So, you may say, why is this important? Once it's cracked, it is cracked. But the thing is, solder joint connections, they actually start cracking in the first 10% of their life. Yes, the first 10% of their life, they start cracking. So the solder joint connections, of course, it depends on the package. I'm not saying every single one of them, but solder joint connections, in some cases, they spend 90% of their life in crack propagation. So that's when you start noticing a degradation of your electronic device. But this can all be predicted. So solder joint reliability simulations, we get into this a lot. We have the, ANSYS has the advanced material modeling capability to be able to, one of the techniques is called unarmed viscoplasticity, where we can simulate the creep behavior, and you can see how the cracks, once it starts initiating, it's going to propagate. And like I said, sometimes it takes 90% of the life for propagation. But all of these can be, and lately, we have thousands of these solder joint connections, but we can model every single one of them. And it's also important that when you start meshing every single one of these, you may want to copy the mesh on one and duplicate the mesh on the others. And ANSYS has that capability, because you don't want to mesh different solder joints with different meshes. But the reason being, as you know, finite element analysis, some of the results are dependent on the mesh size, and you want to be able to compare what's happening one solder joint to the other. So you want to use the same mesh size. And because then once we mesh it, we subject it to temperature cycling. And due to temperature cycling, this is when we can predict its creep or viscoplasticity behaviors. And then we also have, we can also model water and contaminants like dust gathering and how it affects the solutions. For these, we can use ANSYS fluent solutions, and we can also use ANSYS mechanical solutions to look into dust contamination. And with flexible PCBs being used a lot these days, you want to be able to do the process simulation. What do we mean by that? We want to be able to look into the plastic strains that are being developed on these traces, because these flexible PCBs, they are going to have a finite life, since they are very thin and you have these copper layers or metallic layers in them. It's going to start developing plastic strains right away as soon as you start bending them. So you want to be able to model that. And we use this, what's called this mesh morphing approach with these flexible bodies. What that means is that you can actually morph the mesh as these flexible PCBs go into extremely large deformations. And one thing I'd like to talk about is this mesh morphing approach. We use this a lot in solder joint reliability. I'll give a very simple example. This is a technique that's implemented in ANSYS. It's called RBF morph, and what we are doing is mesh morphing. And in this case, you basically model the assembly, the solder joint connections here, where we have the solder balls, we have a substrate mold compound, we have a die underfill, and the PCB. And then we do a simulation. We come up with the stresses and see where the stresses are high in this case. And in this case being, it's just the temperature is brought up to a higher temperature, and the stresses go up in the solder joints. So we know that the stresses are going to go up. Our objective is to minimize the maximum value of stress in the solder balls. And to be able to, this is a demo problem, that's why it is a simpler demo problem, because we want to run a lot of cases really fast. So the objective is to minimize the maximum value of stress on these solder balls. We want to look at the variation of solder ball radius, the solder ball radius, and we want to look at different radii at the top radius, different than bottom radius. So we basically have three variables. The ball radius, the top radius, and the bottom radius. We want to be able to see, by doing this mesh morphing, how does the stress change as a function of time. And normally, if you want to do this, you create your geometry parametrically, you mesh it, you run the simulation. This would be the procedure to do this. However, using this RBF morph technique, you create the parent geometry, you mesh it, then you morph the mesh. You don't remesh it, but you just morph the mesh and run simulation. So you do this cycle instead of going back and doing the geometry again and remeshing again, which is really, you do waste some time over here, definitely. You basically use the same mesh, but you just keep morphing it, you changing the mesh. And then we did this simulation. Since we're running out of time, I just want to get to the result. This is where we started, and then we reached an optimum solder joint connection, just like you see here. This gave us a stress distribution that resulted in 21% reduction in stress. So as you can see here, this is the different solder joint shape right now. So if you want to reduce the stresses, then you want to use a different solder joint instead of using a spherical. So anyway, I just wanted to go through and deliver the ANSYS solutions in addressing mechanical reliability. to avoid component and assembly failures. We do these simulations, and with these simulations, we can assess issues such as delamination, component cracking, and we can also reduce costs associated with physical testing by running simulations to explore and validate design solutions. So 2 weeks ago, we talked about electrical reliability, where ANSYS, SI wave, and HFSS were introduced. And then thermal reliability. Last week, we talked about ANSYS mechanical, ANSYS IcePack. And today, we talk about mechanical reliability, where ANSYS mechanical and ANSYS Sherlock, ANSYS Elastina, they come into the picture. Next week, we are going to talk about reliability physics, which will be mostly on Sherlock. I'm sorry, next week we will be talking about comprehensive multiphysics, where we are going to talk about all these Elastina. How does it work with Sherlock? How does it work with IcePack? How does it work with SI wave? Because, like I said, this is all multiphysics. We calculate the electromagnetic field, which creates heat, which creates expansion, which creates the thermal stresses, and all of these are coupled, and we are going to address that. We are going to talk about those. So again, that will be next week, Comprehensive Multiphysics, June 30th. Please sign up for this webinar. So thank you for joining us. If you'd like to learn more, if you'd like to get a more detailed demo, please contact us 408-732-4665. Our general email address is info@ozeninc.com, and our website is www.ozeninc.com. So I'm going to stop the recording.